Hi, I'm Giuseppe, and I'll present our new paper introducing MatSynth, a modern PBR material dataset. Throughout the presentation, you will find the QR code linking to the project page in the top right corner. Materials play a central role in 3D graphics, describing light interaction with surfaces, which is crucial for realism in games, simulations, and movies. However, synthesizing materials is challenging. Procedural methods need expertise and time, while capture techniques rely on costly hardware. Deep learning offers an alternative solution, but training of these methods demands extensive data. To tackle this, we developed MatSynth, a dataset that enhances learning-based material synthesis with high-quality, physically-based rendering materials. With learning-based approach, data is key, but the largest publicly available dataset by Deschanter et al. Falls short in resolution and diversity, in particular when compared to private company-owned datasets. Our work aims to bridge this gap, providing a new large-scale dataset, which meet the needs of modern methods. MatSynth is a large collection of over 4,000 unique materials. It provides comprehensive material representation, including diffuse, mesostructure, and specularity. Additionally, it offers fine data annotation with descriptive tags and material captions. As you can see on the right, it includes a wide variety of materials. The collection process involved gathering over 4,000 materials under permissive licensing to cover a broad spectrum of materials commonly used by artists. It resulted in 3,736 unique 4K samples, further enriched with 332 blends of compatible classes. In total, our dataset contains 4,069 unique 4K materials. Each material in MatSynth is represented by a common set of maps, accommodating both a base color metallic workflow as well as a diffuse specular one, thus ensuring compatibility with previous datasets. Moreover, we provide extensive metadata annotation for each material, which includes category, descriptive tags, text caption, physical size when available, and stationarity. We also automatically compute the correct scaling factor for the height by optimizing a displacement factor parameter to match the normal vectors derived from the scaled height map to the ground truth normal map. We augment our data employing three key techniques: blending of semantically compatible materials, rotation and cropping, and rendering. For blending, we defined sets of compatible classes, like ground and snow, and use the height maps of the two materials to compute a blending mask for a realistic transition. Rotation and cropping involved extracting crops at multiple scales and rotating the material 8 times with a step of 45 degrees. Finally, we rendered each material with 5 different ambient lights to obtain self-shadowing from the height map while preserving specular reflections and pixel matching with the maps. We split rendering into 2 passes, one for diffuse with displacement using orthographic projection, and another for specular with perspective projection. Our dataset consists of 13 classes of materials plus blends. The bar graph shows the distribution of material classes, comparing it to the data from Deschanter et al. Of the 4,069 materials, 3,061 are stationary and 1,008 are non-stationary. Stationarity is computed extracting 8 random crops from the base color and height map and comparing the clip cross similarity matrix. Finally, the pie chart shows the methodologies used to collect the materials in our dataset. We evaluate the improvements introduced by our dataset on 2 tasks: SVBRDF estimation and material generation. For estimation, we compared Deschanter et al. 2018 and SurfaceNet Vecchio et al. 2021 when trained on the dataset by Deschanter et al. And on MatSynth. MatSynth significantly improves the performance in terms of root mean squared error between predicted and ground truth maps. Perceptual metrics on the rendering further confirm the improvements introduced by the training on MatSynth. We also evaluate the improvements introduced by MatSynth on material generation. For this task, we compare the performance of MatFuse, a recent diffusion-based model from Vecchio et al. As shown in the visual comparisons, training on MatSynth results in improved visual quality and diversity, with the FID score computed on 1,000 renderings further confirming it. In conclusion, MatSynth is a robust dataset of over 4,000 materials, offering extensive annotation in metadata and more than double the size of previous datasets. It is a significant step to improve material data accessibility. Thank you for your attention. Visit the project page for more, including the link to the dataset release.